Okay, this is the video for differential equations, section 7.2, day 2, where we're going to talk about how you can employ Laplace transforms and inverse Laplace transforms to solve differential equations, which means first we have to talk about the Laplace transform of a derivative. So what would happen if I have a function, I take a derivative of it, and then I take the Laplace transform of that derivative, like the Laplace transform of the derivative of f of t? Okay, so we can go back to the definition of that and just apply the definition with the f prime of t here, right? We would have e to the st f prime of t. I don't know what this is, so I'm trying to find something that'll be true no matter what this function is. But I have some function where I've taken the derivative, and now I want to take the Laplace transform of the derivative of the function. So I could solve this potentially with by parts, right? If I were to to make e to the negative stu and f prime of t dt dv, then that means du would be the derivative here, which is negative s e to the negative st dt. And the v would be the antiderivative of f prime, which is f of t. And plugging that into the by parts formula, uv minus integral v du would give me e to the negative st f of t minus the integral of f of t times negative s e to the negative st. And this is an integral in t, treating t as the variable, so temporarily the s is considered a constant, so we could bring it outside. Negative negative makes it cancel. And that means that we would be taking plugging in 0 and infinity, essentially, right? So going from 0 to infinity on this term, and 0 to infinity on this term. But what that means is this right here, this integral right here, is in fact the derivative of, or this is the derivative that corresponds to the Laplace transform of the original function before taking a derivative. So what happens if I plug infinity in and 0 in here? Well, if you plug infinity in here, you get e to the negative infinity, which is going to force this term to go to 0, right? No matter what the function is here. And then there's a couple of constraints here. I guess this function can't be going to infinity faster than this function is going to 0. But in general, this term goes to 0. And this right here would just be e to the 0 times f of 0, which is f at 0 times 1. So what you get is that if you take the Laplace transform of a derivative of a function, you get s times the Laplace transform of the original function minus the initial condition of the function. Right, so kind of interesting that the derivative is just the original Laplace transform with an extra s, but you have to subtract off y0. And if you took a second derivative and just took the results from before, right, the second derivative, right, you would get, again, integration by parts here. You end up getting something where you get s times the Laplace transform of the first derivative. And then when you plug in infinity and 0 again, things cancel such that the derivative of the Laplace transform of the second derivative turns out to be s times the Laplace transform of the first derivative minus the first derivative evaluated at x is 0, or t is 0. And then if you substitute from the previous result what the Laplace transform for the first derivative was as s times Laplace transform of the original function minus f of 0, you get that the Laplace transform of the second derivative is s squared times the Laplace transform of the original function minus s times the function at 0 minus the derivative of the function at 0. So the two initial conditions for the initial y and y prime. And this pattern actually continues. You can show that this continues. So in general, the nth derivative, the Laplace transform of the nth derivative of a function is s to the n power times the original Laplace transform of the original function minus 1 less s times f0 minus 1 less s times f prime, and so on, until finally you're taking the f minus 1 derivative and plugging in 0. So you can summarize it this way. Laplace transform of 0 is 0. The Laplace transform of a function y is y, capital Y. The Laplace transform of y prime, the derivative, is s times y, but minus y at 0. The Laplace transform of second derivative is s squared times y, the Laplace transform, minus s times y of 0 minus y prime of 0. And just to continue the pattern, the Laplace transform of the third derivative of a function is s cubed times ys minus s squared times y0 minus s times y prime minus y of 0. That actually should be a y double prime. Mistake in the notes there. Okay. So now that we know how to take Laplace transforms of derivatives, it implies that if we were given a differential equation, we could take the Laplace transform of both sides of the equations. And this is why we're studying Laplace transforms in a differential equations class. The reason that Laplace transforms are so powerful is when derivatives are transformed, you end up getting algebraic equations, which means then you can solve for y of s just using algebra. And then when you get what y as s is equal to, you just take the inverse Laplace transform to convert this into the solution y. So a little procedure would be take the Laplace transforms of both sides of a differential equation, solve algebraically whatever you need to do to get ys, the capital Ys, the Laplace solution, and then take the inverse Laplace transform of both sides to get yt. This is really where Laplace shines. Let's take an example so you can see what we're talking about here. Let's say we have this differential equation 2y prime plus y equals 0, and we have the initial condition y0 is -3. Now we have a lot of methods we could use to solve this, but let's show how we could use Laplace transforms. Okay, so what we'll do is we'll take the Laplace transform of both sides of this equation, right? So first we have 2 times the Laplace transform of y prime. That's a first derivative. And so that means using this, Laplace transform of derivative is sys minus y0. So I'm just going to replace that y prime. The Laplace transform of that is s times Laplace transformed ys minus y0. And then I'm going to put plus y, but we're going to take the Laplace transform of that term. And the Laplace transform of y is just capital Y of s. And then over here, the Laplace transform of 0 is 0. Okay, so we take the Laplace transform of the entire equation, both sides. That forms an algebraic equation, no derivatives now. Now all I have to do is solve this algebraically. But before we do that, we're going to substitute that y0 is equal to -3. So now I have 2 times s times ys minus, or I have 2 times, let's say minus is plus 3. So that's 3 times 2 is 6 plus ys equals 0. And I'm going to now solve this algebraically for y. I'll gather the y terms together. So I have 2s plus 1 ys terms plus 6 equals 0. So if I move the 6 to the other side, then ys is -6 over 2s plus 1. And now, if I take the inverse Laplace transform of both sides of this side just becomes y of t. That's my solution, y. And now I have to do my inverse Laplace transform here. So I go trying to find this. This looks like, let's see, we have an s and a number here. So first I could say that this is equal to -6 1 over 2s plus 1. I could say this is -6 1 over and factor out the 2 on the bottom and make that s plus 1/2, right? That would be okay. And then if I then said this is -6 and then that's a 1/2 times 1 over s plus 1/2, that really means we're talking about -3 1 over s plus 1/2. So I'm going to take the inverse Laplace of that. That's -3. And the inverse Laplace of 1 over s plus 1/2 is e to the -1/2 t. Okay, so now that I have that, that's my solution. Done. Instead of all those methods we learned earlier, we could have done this way. Remember how we used to have to do this using a method? Maybe we would use the 2m. In fact, let's do one just to see that it comes out to be the same. Let me erase a little spot here. Let's do it using older techniques. So we could say, hey, linear differential equation, homogeneous with constant coefficients. I could use a characteristic equation, 2m plus 1 equals 0, which means 2m equals -1, m equals -1/2, which means the general solution is the form y equals a constant e to the 1/2 t. And then I could plug in my initial condition, -3, when t is 0 to get that c is equal to -3 and write this as y equals -3 e to the -1/2 t. Right, so we had methods, right, that would solve this. This is another method. We could transform everything using Laplace transforms, solve algebraically for y, capital Ys, and then do an inverse Laplace to get the solution. Okay, the beauty is that we can take Laplace transforms of stuff on the right-hand side that we don't have any way to deal with yet. So we'll see more examples of that later. Turns out to be a very powerful technique. Okay, let's look at another example. What if we had this differential equation with a third order derivative? So let's take the Laplace transform. The Laplace transform of a third derivative is, that is s cubed times ys minus s squared times y0 minus s times y prime of 0 minus y double prime of 0. So you keep going up in derivatives and down in s's. That's the y triple prime. Plus 2 times y double prime, which is s squared ys minus sy0 minus y prime of 0. And then minus y, that's y double prime, minus y prime, which is, I'll continue down here, minus, and then y prime is going to be s times ys minus y0. And then minus 2 times y, and the Laplace transform of y is just the ys. Okay, and then now here on the right-hand side, instead of employing all those crazy lookup tables and everything, we can just take the Laplace transform of sine of 3t, which is itself a lookup table. So if you use a table, sine of 3t transforms to sine is going to be 3 over s squared plus 3 squared. So we'll get 3 over s squared plus 9. Okay. And then what I can do is I can gather all the terms on the left-hand side that have a ys. So I've got s cubed from this term, and I've got a plus 2s squared from this term, and I've got a minus s from this term, and I've got a minus 2 from this term. That's the ys's. And then let's go ahead and plug in some numbers here because they gave me all these initial conditions. So y of 0 is 0, so all of these are going to be 0. That's a 0, that's a 0, that's a 0. And y prime of 0 is also 0, so this is a 0, this is a 0. And then y double prime is 1, so this one right here is going to become a 1. Okay, so I do have another thing here, right? From here I've got minus 1. I've already accounted for that. These all canceled. This was already used. So we've got all of that equals 3 over s squared plus 9. Okay, so now don't forget to move this over to the other side. We would have s cubed plus 2s squared minus s minus 2ys equals 3 over s squared plus 9 plus 1. Okay. And then we're going to divide. Actually, you know what? Let's get this to be one fraction because I'm going to have to divide by this. It'd be much nicer if I just was dealing with one thing over here. So let me get a common denominator over here. This is 3 over s squared plus 1 plus s squared plus 9, over s squared plus 9, which means it's 3 plus s squared plus 9 over s squared plus 9. So it's just s squared plus 12 over s squared plus 9 here. So a little bit of algebra manipulation over here. And now when I divide by y by this multiplier here, ys is, we have s squared plus 12, and then we have over s squared plus 9. But then when we divide by this, we're dividing by s cubed plus 2s squared minus s minus 2. All right. So now I've got everything solved for my capital Ys. To solve the differential equation, we just need to now take the inverse Laplace transform of everything. So the left side's just going to become y of t. And then I'm going to go ahead and just plug this all into the online calculator. So let me do that. You can follow along here or do this on your own. We're going to go up here to the fraction, and I'm going to enter, let's see, s squared plus 12 on the top, s squared plus 12 on the top. On the bottom, it's like we've got s squared plus 9 in a parentheses, so s squared plus 9, and then times another quantity, s cubed plus 2s squared minus s minus 2. And we'll let them do the hard work of figuring out what this expands into separate terms. Okay, so it looks like we've got this result here. Let me write the result. So this is 3 minus s over this. I think I'm going to split that up. Yeah, because you can think of this as s over s. Yeah, let's split that up. So the way I would interpret that, let me see if I can bring this down here so I can write on it. I want to scroll up here. Okay, so the way I would interpret that is this is the same as they wrote, I'm just going to write it first, 3s minus 6 over 130 s squared plus 9 plus, this is what comes out of the partial fraction calculator, and then I'll show you how to interpret, minus 13 over 20s plus 1. Okay. Plus, there's another term, plus 13 over 60s minus 1. All right. So let's go ahead and work with that then. All right. So we're not quite ready to do the inverse Laplace just yet. We have to do a little bit more massaging. All right. So the first thing I would do is say this first term here, so we have y of s is 3 over 130, and then it's s over s squared plus 9. That's 3 over 130 s over s squared plus 9. Okay, and then I've got minus 6 over that same thing. So that's going to be minus 6 over 130, 1 over s squared plus 9. And then I've got this plus 16/39, 1 over s plus 2. I've got minus 13/20, 1 over s plus 1, and then plus 13/60, 1 over s minus 1. So you want to try to write these things as constants times something that you can match in the table. And most of these are already ready to match. I think there's one fix-up we're going to have to do here, and that is that this one is almost what we need for sine, except that this has to be a 3 up here, so that this is 3 squared. So we're going to put a 3 down here as well to compensate for it. All right, so let's go ahead and do the inverse Laplace now. So the inverse Laplace transform of the left side is y of t. And then I've got 3 over 130, whatever s over s squared plus 9 is. Right, so s over s squared plus 9 is in the table to look up for that 9 is 3 squared. So it's 3t. Okay. And I've got this, let's see, this 6 and this 3 will combine to become a 2 over 130, which is the same as, well, let's just do that in a calculator. 6 divided by 3, but then divided by 130. The simplest way to write that fraction is 1 over 65. Is that right? I have a 6 there? Yeah. Okay. So 1 over 65. I had to have that 3 there so that this would transform into the right form for sine of 3t. Then I've got 16 over 39. This is the right form for e to the negative 2t. And I've got negative 13 over 20, and this is the right form for e to the negative 1t, right? And then this one is 13 over 60 times the form for e to the positive 1t, so just t. So this is the general solution, and hopefully you can now start to see the power of this, right? Compared to what it would take to solve this the other ways, well, I don't know, that would still be solvable with methods that we know. All right. So that's the last example I have for you today. You'll have to just try this out, but you can see the idea. We've got the Laplace transform, and then we also have uh, the important list of the ways you transform derivatives, right? Okay, that should be it for the lesson for today.